So this is going to be your lecture for October 6th. Today's lecture is going to cover quite a few different topics, but let's go ahead and start with the most basic, and that's going to be looking at your Lewis dot diagram. And your Lewis dot diagram is going to represent the number of valence electrons. And if you recall from our last lecture where we were talking about our Bohr models, valence electrons are your outermost electrons in your Bohr model. And valence electrons, they had a trend. First family had 1, second family 2, family 13, 3, all the way to 8. 8 starts at neon. Helium was the only exception. Helium only has 2 electrons, so therefore helium will only have 2 valence electrons. So this was our general trend. So from here on out, when we're asking about valence electrons, all I have to do is find it on the periodic table and tell you, oh, here's silicon, element symbol Si. It's in family 14, so therefore it has 4 valence electrons. Same thing with bromine, Br, family 17, so therefore 7 valence electrons. Sodium or hydrogen, those are both in family 1, so therefore those will have 1 valence electron. So those are simply a trend. You find them on the periodic table, and you're able to look up at the top here and determine your valence electrons. How it ties in with our Lewis dot diagrams is going to be as so. X is going to represent any possible element, and my little dot here is going to represent my valence electron. So if I'm in the first family, I'm just going to have my element and a dot. So again, first family, if I'm looking at hydrogen, my valence electron, or my Lewis dot diagram, would simply be hydrogen with a little dot above it. If I'm looking at my second family, you will have the element with 2 dots. So let's look at magnesium. Simply have 2 dots. So in the long run, when we're going through with these, it doesn't matter where the dots are placed. What matters is, do you have the correct number? So if I'm wanting to continue and look at calcium, I have 2 dots. It's the same thing right here. It's telling me that I have 2 valence electrons. So I'm not going to be counting those kind of answers incorrect, because you are simply telling me that there are 2 valence electrons. So don't judge yourself too harshly there. When you're in family 13 and you're looking at your family with only 3 valence electrons, 1, 2, 3. So we can look at aluminum, Al, 1, 2, 3. Family 14, so that means you would have 4 valence electrons. So if we're looking at carbon, make this a little bit bigger there. We're going to continue down. That was family 14, so there was 4 valence. So right here would be 5. 1, 2, 3, 4, 5. This would be family 15, so nitrogen is a good example here. Family 16 will have 6. 1, 2, 3, 4, 5, 6. So we'll look at oxygen. 1, 2, 3, 4, 5, 6. Family 17 should have 7. 1, 2, 3, 4, 5, 6, and 7. And that would be family 17. So fluorine, chlorine, bromine, iodine, any of those will work. 4, 5, 6, 7. And last but not least, our noble gases. You will have a total of 8. So let's look at argon, AR. 7, 8. So I have a total of 8 valence electrons. So I have placed 8 dots around my atomic symbol. So this is what your Lewis dot diagrams look like. So that leads us into our next part of the lesson, where we're going to be looking at the type of bonds. So kind of starting off, one bond is going to be equal to a total of 2 electrons, because a bond is represented by a single line. So one end has an electron, and therefore so does the other. So that's where we get our total number of electrons for a bond from. And there are 2 different types of bonds we can make. We can make a covalent bond, which is between a nonmetal and a nonmetal. So that's like 2 fluorines. Or if we're going to go ahead with C and O, nonmetal, nonmetal. If we're looking at phosphorus and sulfur, so these would all be considered covalent bonds because they are 2 nonmetals coming together. I can also have ionic bonds. Ionic bonds are our most popular bonds that we actually have. And that's between a metal and a nonmetal. A metal will have a positive charge, and your nonmetals generally have a negative charge. So these charges are why metals go first and nonmetals go second. And so ionic bonds are going to be like sodium chloride. Sodium is a metal, and chlorine is your nonmetal. I have no idea why I wrote a B there. So Nb, nonmetal. And again, this is going back to our periodic table. Remember where we had our staircase of metalloids? Anything that is up to the right, this is all going to be non-metal. So oxygen, fluorine, argon, even helium, that's an exception that's over here. All of those are non-metals. Everything else that's to the bottom, to the left, these are all going to be considered your metals. So that's where we get the concept of sodium. That's why it's a metal. That's how it's all classified. So let's go ahead. If I have potassium and fluorine, potassium is a metal, fluorine is a nonmetal, so therefore their bond is a ionic bond. So taking this knowledge and moving forward, we're going to look into the structures. So if I'm looking at a covalent bond, my electrons will be shared. I'm going to underline shared here because that's actually very important. Covalent bonds are going to share their electrons. And they're not going to just share an infinite amount. There is a magic number of 8. You want 8 electrons. Every element except for hydrogen and helium. Now I'll go ahead and put that up here. Except hydrogen and helium. Every element wants 8. That is the magic number. So if I have a covalent bond of 2 iodines, the first thing I'm going to do to actually write this out and describe it is I'm going to look at my periodic table, and I see iodine is right down here, and it has 7 valence electrons. So I'm going to draw out 7 valence electrons for each iodine. Both of these iodines only want 1 more electron to get to that magic 8 number. So what's going to happen is they will share this electron. So my green right here is going to be the bond. So they are going to share that electron. And that means right here, 2, 4, 6, 7, 8. This iodine has 8 electrons now. If I'm looking at my other iodine, this iodine is now sharing 1, 2, 3, 4, 5, 6, 7, 8. So that is our covalent bond. Now, there is a little issue. There's always a little something extra added on to this. And that with covalent bonds will come double and triple bonds. Yeah, I know that's spelled wrong. There you go, triple, Triple. If I misspelled it, you can send me an email. I don't care. But you have double and triple bonds. So double bonds will end up looking like an equal sign. And there's 4 electrons will be used. Triple bonds will look like a stack of pancakes here. 3 lines. Remember, each line represents 2 electrons because each is a bond. So 2, 4, 6 electrons will be represented in a triple bond. And there are only a certain amount of elements that can do that. Carbon, nitrogen, oxygen, phosphorus, and sulfur. We call them CNOPs. These are the only 5 elements that can produce both double and triple bonds. And they are only going to be there for covalent bonds. That's when it's between 2 nonmetals. So keep that in mind. This is actually from the worksheet. So we're going to look at oxygen and carbon dioxide here. Those are the 2 problems that we're going to work out together that will show your double bonds. So your first step is to draw out your elements. So I have oxygen and oxygen. I know to look at the periodic table, oxygen is in family 16, so therefore it has 6 valence electrons. So I'm going to draw out 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So by looking at these here, I'm going to think to myself, if I need 8 electrons shared and I have 6, how many more do I need shared with me? And my answer should be 2. So I take the 2 that I need right here, and I know that somehow I'm going to have to share these. So I need to make 2 bonds to get those 2 electrons. So oxygen, oxygen, 1, 2, 1, 2. And I'm creating my 2 bonds. So technically I have these 6 that were there, but now I'm sharing 2 more. So now I have a total of 8 electrons. 2, 4, 6, 8. Same thing with my other oxygen. It technically still has the 6 that's close to it, 1, 2, 3, 4, 5, 6, but it is sharing 2 electrons from the other oxygen. So 1, 2, 3, 4, 5, 6, 7, 8. So therefore, each oxygen is still happy. Same with CO. Carbon will have a total of 4 valence electrons. And again, we got that from the periodic table, family 14, so 4 electrons. And I know that we're going to have a bond here. And each oxygen will have a total of 6. So 1, 2, 3, 4, 5. Let's just put it right here. 6. 1, 2, 3, 4, 5, and 6. So looking here, I have 4 around carbon, and each oxygen has 6. Our goal is to get every atom with 8, because again, remember, 8 is that magic number. So 1, 2, 3, 4, 5, 6. I have 1 bond here, so that makes 7. So I need 1 more electron. That's where I will create another bond from my leftover electrons. Same with this one. If I have 1, 2, 3, 4, 5, 6 electrons, and this bond creates 7, I'm short 1. So that's where my electron comes down. And I know I'm going to share this. So my final molecule, my final shape, should look something like this right here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So these are just examples of what our covalent bonds look like. So your homework, this is just one page, is to show what the other shapes look like. How would you draw them out? And to be honest, you're only going to have 4. That's your only other one that may look a little strange. And I'm going to tell you this, that one's going to have a triple bond in there, because you're going to want to make sure that each nitrogen has a total of 8 shared electrons. So let's look at your ionic bonds now. Ionic bonds are going to be a transfer. So ionic bonds are a transfer of electrons. That means that it's just going to give it away. So if I have NaCl, sodium will have 1 valence electron. It's in that first family. Chlorine will have a total of 7. because it's in family 17. So sodium will just give away its valence electron because it's easier for sodium to give one away than it is for chlorine to create one. So that'll give me NaCl, and this right here, that's my bond. That's why ionic compounds are so close, is because their bond is through a transfer. You're simply giving it to another. So if I look at my ionic bonding, this is still part of the handout. I have BES and question 1. They both kind of go the same way. If I look at Be on the periodic table, Be is right here, so therefore it has 2 valence electrons. So Be, 2 valence electrons. Sulfur, family 16, will have 6 valence electrons. Remember, 8 is that magic number. It's easier for Be here to give up its electrons and create an ionic bond with sulfur here. Where this is our bond, sulfur now has 8 electrons, and Be is just kind of hanging around watching to see how sulfur is using its electrons. Same thing if I look at Kf, potassium, K, first family, 1 valence electron. Fluorine, family 17, so therefore it has 7 valence electrons. Same thing as kind of like NaCl. So that leads us into our next small topic of charges. Charges are, again, it was a trend on the periodic table. Whether or not we remember or not, that's a different story. So let's kind of review that one. Family 1 will always have a charge of +1. Family 2, +2. Family 13, +3. Plus -4, -3, -2, -1, 0. So noble gases are actually always happy. They don't have a charge. Family 17 with 7 valence electrons. Since it's short 1 electron, that's where the -1 charge comes from. Same thing with family 16. Valence electrons are 6. It's short 2. We work our way to the plus or -4. This completely determines if it's bond with another positive or with another negative. It's completely dependent on what it's bonded with. When we get to family 13, it's easier for family 13, 1, and 2 to give away our electrons, so they're more ready to give away their extra valence electrons, which is why they're positive. Family 13, since it has 3 valence electrons, it means that it has 3 electrons that it's willing to kind of just give those electrons away. Same with families 1 and 2. They're ready to give away those valence electrons, so therefore they have a +1 and +2 charge. So if I look here, calcium, Ca, its family has a +2 charge, so therefore calcium will always have a +2 charge. Aluminum, Al, family 13. Family 13 always has a +3 charge. Oxygen, -2. So what I'm doing up here is I am taking my elements now and I am writing out what is called ions. Ions will have charges. That's what they are. So if I take these ions, and I'm going to put one more up here, one with a negative charge. Let's look at Br. And again, you're looking at the charge. We're going to make some ionic compounds. This is another reason why ionic compounds are called ionic, is because of your ions. Because calcium and aluminum here are both metals, while oxygen and bromine here are non-metals. Remember, ionic bonds are metal, non-metal. So if I take calcium here and bromine, Br, and I want to make a compound, I wouldn't just write out this is wrong. That's not how I would write it out. We would simply take the numbers from the charges and crisscross or drop and swap. So I would take the number and bring it down. So I would have Ca, and my number that's brought down here is 1. Br, my number here is brought down from my charge, so I would have 2 that's brought down. So technically in chemistry, we don't like writing ones. That's just the way it goes. So when you write a 1 here, it's technically not acceptable. I'm not going to count it wrong in physical science, because y'all are still learning. But technically, you would write it out CaBr2, because technically calcium is already there, so you don't need to write a 1. But for bromine, there's 2 that need to be present. So therefore, the 2 needs to be written. Now, here's where it comes to play, is ionic compounds will always end up having a 0 charge overall. So if you're wanting to look at this in a different aspect, if I have bromine with a -1 charge, how many bromines would I need to cancel out 1 calcium with a +2? So I would have to draw out another bromine here. So then that way I would have 2 bromines, so I would have 2 -1 charges, and that would cancel out my 1 calcium. So overall, my charge would be 0 with CaBr2. Overall, this is 0 charge. If I'm wanting to look at another example, so I'll put up here example 1, and down here example 2. If I'm looking at aluminum with a charge of +3, and let's go ahead and move this, and oxygen with a charge of -2, what final formula would I have? I would have to complete my drop and swap, or your crisscross, whatever you want to call it. But you're looking at Al, take the number, not the negative, you don't need that, you just need the number. So Al2, oxygen, you take the number 3. So my final compound would look like this. So our homework, this would probably be the 4th page, if I'm remembering correctly. And let's go ahead and grab that copy. I left it on the other side of the room, so give me 1 second. So you have one worksheet that looks like this. All you're doing is the exact same thing. So let's look at our compounds here. NH4, plus 1, and CO3 minus 2. All you're doing is you're taking the numbers and you're dropping them. So I should have NH4, the 2 coming down. Now if I write 2, that kind of looks like the number 42. So I'm going to make sure to add parentheses so I know that we're talking about I'm needing 2 NH4 and not that I have 42 hydrogens. So NH4, my 2 comes down, CO3, and 1 comes down. Now remember, 1s are invisible. We kind of assume that they're already there. But if you're wanting to put a parenthesis around CO3, again, that's completely acceptable. However you want to display that. The only thing is if you put a 1 next to the 3 right here, it would look like it says 31. So if you're doing that, please make sure that you put parentheses. So let's look at NH4 and PO3. NH4 has a positive 1 charge. And so let's again write this one right here. PO4 has a charge of minus 3. So the numbers are crisscrossed, drop and swap. So I had to have NH4, 3, PO4, and again, this is a 1, so you can either write it as is right here, or you can put parentheses and put the 1. So it's kind of matching your positive to your negative, and you're filling in the blank. And as you go along, that's all that you're doing. So Na, SO4, drop the charges and swap them. So Na is our positive. I know that this would be dropped, so Na2, SO4, this is a 1, so we're not needing to worry about it. Same thing here. My 3 will come from the charge, PO4. So this is generally everything that we're doing today. Today is a lecture-heavy day, and the homework that you're assigned in Google Classroom is really just a lot of practice. I know it's super easy to look up these answers on the internet, but I beg of you, if there's a problem that you want specific help in, let me know and we can actually go over this for my virtual students. Because in the next couple of days, the assignments that are going to be assigned are going to reinforce this one lecture. So if you have any questions, please let me know. But really, all I'm expecting from this first day is I'm expecting for you to have, 1, at least listen to the lecture, and 2, attempt the work. So then that way, next class, we can kind of go in and you can say, hey, Ms. Kang, number 2 on the first worksheet was kind of strange. Could you please work that one out for us? And then we'll be able to kind of work that one out and we can continue to learn on this lesson. So if there are any questions, please email me. Other than that, make sure you have a wonderful day.